Our next example has us examining the value of the rate constant at 430 Kelvin units. So now we're being asked to solve for a rate constant K. We have the same generated list. K varies with temperature. Again, we're going to use our non-graphing form of the Arrhenius equation. We'll set up what we know so far. The natural log of the rate constant K1 over K2. I'm going to keep the first value for K1 that we used up in the original problem from the first line, 2.52 times 10 to the negative fifth per seconds. K2 is what we're solving for to match that 430 Kelvin. 430 Kelvin units is our target temperature. Now the activation energy we just solved for up above in the previous problem. Again, that solution was given to us. Notice I answered in a kilojoule, but we must plug in activation energy in a joule unit for our problem to match the 8.31 metric R constant. So that large activation energy reported back in a joule, 158,605.56 joules of energy, set over the gas constant 8.31. The temperature that corresponds to T2, the T2 temperature is our target, 430 Kelvin units, minus the T1 temperature coming from our first line of the data table, but in a Kelvin unit, 1 over 462.7 Kelvin units. Notice K2 is our target variable. Let me again switch the paper to show my step-by-step solution of pulling out K2. Putting back into the equation, here's what we had just a moment ago. This is just recopied from the note pack, the natural log of K1 from the first line of the data table over K2, set equal to our activation energy solved for just above in a joule over the R constant 8.31, and the comparison of temperatures 1 over 430 minus 1 over 462.7. What I then did was just took my time and I simplified the right-hand side of my equation. I divided the joules by 8.31 and multiplied by the reciprocal of those two temperatures. When I did that, I found the right-hand side simplified to 3.136. So what we have on the left, the natural log of K1 over K2 set equal to 3.136, the simplified answer from that math up above. That's just hitting it out on the calculator. To get rid of the natural log, we take the inverse natural log, which is Euler's number, that second function ln. That's where you see the e value sitting on top of on your calculator. To simplify, to get rid of that natural log, that's e raised to the 3.136 equals what was left inside of the parentheses, 2.52 times 10 to the negative fifth. That's the value for K1 over K2. And again, what we're doing is to get rid of natural log, we take the inverse natural log, which is the e, Euler's number. E raised to the 3.136 now equals the ratio that was inside the parenthesis. Simplify e raised to the 3.136. Hit that on your calculator. It will read 23.0317. That's still equal to that ratio of K1 over K2. And finally, when we pull out K2, what happens is those two things just switch places. The 23.0317 and the K2 will just switch. So I end up hitting for K2 2.52 times 10 to the negative fifth. That came from the first line's data table. Set over the answer, 23.0317. And our final answer for the rate constant K2 at our temperature of 430 Kelvin came out to be 1.09 times 10 to the negative 6 per seconds.